We are now into video lecture 26, and we continue our discussion on progressive metamorphism of siliceous dolomite or dolomitic quartzite. I will read out the diagram once again for the benefit, but without the fluid component, so it becomes less clumsier. So that's the reaction. I will just put in the numbers once again. We are here now, so this is the diagram that I initially drew. We discussed in detail about this diagram, and when I was talking to you in the last video lecture, I talked to you something like closed system metamorphism, meaning that closed system, the temperature, the system and the surrounding exchanges temperature, but there is no mass transfer across the system surrounding interface. So essentially, the composition of the system does not change. It does not mean that the mineralogy and the fluid composition remains the same. Only thing, the summation of those, whatever changes are, the summation of those will give you the same chemical values of the components before and after, the system components before and after. It's going to be a uniform composition. The only thing that doesn't change is composition. The temperature, the pressure, the fluid composition, everything changes. But what it doesn't change is total bulk composition. Now, we have seen that we can have in this model, we have talked about closed system metamorphism, by which we have also realized that you can change the bulk, if you change the bulk composition, or if you change the bulk composition, then the reactions change systematically. If you change the fluid composition for the same bulk composition, the reactions that happen are different. So there is a large control of how the reactions progresses in time with progressive metamorphism is a function of both the bulk composition as well as the fluid composition. Nothing is less, nothing is more. Especially in systems where the reactions are not fluid-free reactions. They are all reactions in which fluids are involved. Now, so we will now talk a little bit about, I will introduce you to this, this closed system metamorphism, when it happens. Say, for example, once again, I will just write this reaction. 5 dolomite plus 8 quartz plus H2O, plus H2O is equal to tremolite plus 3 calcite plus 7 CO2. This is what the reaction is. Here the important point is dolomite plus quartz are the reactants, tremolite and calcite are the products. And you consume the H2O is consumed and is stabilized at the hydroxyl phase of tremolite, and carbon dioxide is released because dolomite decomposes to carbon dioxide, although it involves 3 calcite. What is important here to realize is that while this reaction progresses, the fluid composition goes on continuously changing as the modal mineralogy of the rock also undergoes experiences changing. So the fluid composition here, although we have a closed system, the composition of the fluids which are lodged either within the mineral as structural water or carbon dioxide, like in tremolite it's OH2, in calcite it's CO2, as in CaCO3 you have the CO2. But there is a continuous change in the fluid composition as well as in the mineralogy. And if you look at it, we say, for example, you start with a slightly hydrous material like this, at XH2 quite low, you can see HCO2 quite low, that means it's a more hydrous conditions. And then you move along this path, and somewhere dolomite or quartz gets exhausted, and you produce a mineral. Say, for example, if quartz is there, dolomite gets exhausted, then your PT path is here, and then the path moves to the peak, and then you can have a path like this. So you can have a path like this. You can have a very different path if you have a different fluid composition. So what is happening, the modal mineralogy and the fluid compositions are both changing. Now, let us assume a situation where we go to an area, and there is, say for example, an igneous batholith that intrudes a siliceous or dolomitic, say for example, dolomitic quartzite. Say for example, if this material here is dolomitic quartzite, right? Now if this is dolomitic quartzite, then you can understand one thing. And if we consider that let's say for our discussion that this composition of the rocks, let's say this is north, and let's say this, whatever it is, the scale, say 50 meters, say for example, or maybe 500 meters. Let's say this is 500 meters, so it's quite a bit of distance. And here you have a granite batholith intruding into siliceous dolomitic quartzite. So what happens is the temperature increases in this direction. The temperature increases in this direction. So obviously in this path, the low temperature part should be the farthest, and the highest temperature part should be closer to the granite batholith. The granite batholith intrusion temperature, you can assume it to be somewhere around, say, 700 degrees centigrade, 750. If it's dry enough, the temperature emplacement could be high. It could be varied, but I don't think it's going to be much higher than that. So it's 700 to 800 degrees centigrade, and it intrudes a rock which is 25 degrees centigrade. So what you generate is essentially minerals, high temperature minerals stabilizing close to this, and low temperature mineral further away from it. Now, if you allow closed system metamorphism, then you see what happens from low temperature to high temperature. From low temperature to high temperature. It is radially increasing. What will happen? Say for example, here you will have dolomite quartz, right? Dolomite quartz will be where the temperature does not go above, say 500 degree or 470 degree, you have dolomite and quartz. Then you can see in the rocks here, the rocks that experience this, you will have, say for example, an assemblage here and an assemblage here, and this will have dolomite, quartz, tremolite, and calcite. And that means you are within this temperature field. And then again, there could be a domain where if you start with, say for example, dolomite 10 and quartz 90, dolomitic quartzite. Say for example, as you move to higher temperature, you will have dolomite will be exhausted, and you will have quartz, tremolite, calcite. Do you understand? And then diopside will be added to it. So you have quartz, tremolite, calcite, diopside. When you see in this part we will have tremolite, and one of these phases will get exhausted. It will not be quartz, it will not be calcite, it could be tremolite, because in the reaction it can't be quartz because the rock contains too much quartz in it. So either tremolite or calcite will be exhausted, and you will produce diopside, and somewhere you will have another aureole where possibly tremolite will be exhausted, and you will have calcite, quartz, diopside, and you will have an inner aureole. So the highest material breakpoint, maybe you will have forsterite, diopside forsterite assemblages, diopside forsterite tremolite assemblages in the lower part. So you have what is called contact aureoles, where you have assemblages like this. Say for example, this is high valence assemblage, dolomite plus quartz. But dolomite, quartz, tremolite, calcite is a low valence assemblage. After that, when you again do this, where it goes up here, then you again have a high variance assemblage. Then again you have another reaction by which you produce dioxide. You will have a low variance assemblage, and then again a high variance assemblage. So this red, so we have a succession of low variance, high variance, 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 high variance, low variance, high variance, and you go on doing it. So all these ones which are in blue are low variance assemblages which are separated by low variance assemblages. These low variance assemblages are essentially these segments. These segments essentially represent the low variance assemblage or assemblages with more phases. So you will have a succession of orioles where you have low variance, high variance, low variance. You can also have invariant assemblages if the mineralogy is of a particular type of mineralogy and for a particular composition. You can also have an invariant assemblage. What I am trying to say is that you have a base of low variance, high variance, low variance, high variance, low variance, high variance, low variance, high variance. You will have a systematic variance of assemblages. And these parts, these widths, essentially represent a width in temperature. Can you see that? This is the temperature range. It represents the range of temperatures over which this reaction will happen. And also another thing you would imagine in this assemblage, when you are talking of dolomite, quartz, tremolite, calcite, you can see for here, dolomite, quartz producing tremolite, calcite, it's a high variance assemblage, but the proportion of dolomite from here to here is decreasing. From here to here, dolomite is decreasing. From here to here, quartz is decreasing. But from this side, tremolite and calcite is increasing. The modal abundance of tremolite and calcite is increasing because you're producing more and more tremolite and calcite. Until for a dolomitic quartzite, as I told you, dolomitic quartzite will stay and dolomite will be out of the reaction. So this is the plane where dolomite goes out. So this is the plane which is dolomite out. This is the place where it's dolomite out, and this is the place where you have tremolite in. So this is where tremolite comes in, and here is where dolomite goes out. So similarly here, for example, at this point here, this is dolomite in reaction. But it does not mean something's out. It's dolomite in reaction. So tremolite in, dolomite in, you will have a succession of univariant, high variance, low variance, high variance, low variance, high variance, low variance assemblages till you reach the highest temperatures. And in each of these bands represents a temperature width. These bands all represent temperature widths. Widths over which the assemblages had larger number of phases. That means they represent a temperature interval. Although this is an interval in space because this is a ground, but this represents a difference in temperature. So what you can see is that when you, and as I told you, I assume that the rocks all here have the same composition and the same fluid composition. Same whole rock composition and the same fluid compositions. If I bring in variations, then you will see these lines that I have drawn will also be not valid if you change the mineralogy or if you change the fluid composition. What we are doing is, what we are trying to do here is trying to show that if you have an uniform composition of rocks and they are subjected to high temperatures, then there will be contact metamorphic orioles and they will be arranged like this if it is a case of closed system metamorphism. Closed system metamorphism. Now I will introduce you to something else. Open system metamorphism. Completely open system metamorphism. That means that you have a rock. That means you have a rock which is in contact with a huge fluid reservoir. Huge fluid reservoir. And so whenever you are studying the rock, this fluid, whatever that fluid is of that composition of fluid, it's huge in comparison to the pore spaces that occupy in a rock. In a pore space in a crystalline rock is very small, less than 0.01 volume percent. But if you have a fluid reservoir, and you can ask me, sir, how do I have a fluid reservoir? Say, for example, there is shears, where there are large amount of fluids percolating at any given point of time. So, although the fluid does not exist like a reservoir, but there is a constant influx of fluid at a particular composition. So, what will happen in that case is very crucial. In that case, the composition of the fluid, and remember, I am talking of a big fluid reservoir, constant fluxing of fluids with a particular composition, is completely fluxing the rock. So what will happen? Let's say this is the composition of that fluid. Let's say this is the composition of that fluid. That means HCO2 is 0.25. Let's say the fluid that is fluxing the rock and overwhelming the rock has an HCO2 value at 0.25. Now what will happen? Now you see, the changes in fluid composition here are restricted to the pore spaces and to the mineral structures that they have. But if the rock is in communion with a continuous flux of fluid, then what happens? The fluid composition, therefore, does not change. Or it changes, but relative to the huge volume of fluid that is percolating, the change of the composition of the fluid due to the reaction is also getting fluxed. Remember, they do not get stuck into the mineral, because along the shear zone, the fluid starts to flow around the composition. So what happens? There is a complete fluxing of fluid, but that is fluxed by an overwhelming the buffering capacity of the rock. So what will happen is you will completely buffer the system. So what will happen if this is the composition of this? So whatever you do, whatever your mineralogy is, the PT path will be like this. The PT path itself will be like this. It will not go through these complications that we were talking about. Reactions will happen. Say for example, if you are here, say for example, for this composition, if dolomite plus quartz is reacting to produce tremolite plus calcite, now that reaction will happen. That reaction will happen at this temperature for this CO2. Amount of H2O that is being consumed to produce tremolite, and the amount of CO2 that is liberated because dolomite is decomposing, the magnitude of that fluid is very small, continuous to the continuous fluxing of fluid. So what will happen? What will happen in that case? If I look at this diagram now and draw it, say I draw the same diagram again. If I draw the same diagram here again, this is the same batholith. and placed at the same temperature, and this was the same rock, dolomite plus quartz, what would happen? You can see from here. You will first have dolomite plus quartz. My pens are all not working, it's making my life miserable. If you have, say for example, if you have dolomite plus quartz, so dolomite plus quartz would react to produce dolomite, quartz, tremolite, calcite. And since we are talking of this, we can imagine dolomite will get exhausted and quartz, tremolite, calcite will come in. So now you can see once you have quartz, tremolite, calcite at this temperature, there will be a reaction and you will produce quartz, tremolite, calcite, dioxide. Again you see high variance assemblage, smaller number of phases, then low variance assemblage, then high variance assemblage, low variance assemblage. Again the same thing happens. But there is a difference. If in the class I normally ask the student, what is the difference? So will I get the same map? Will I get the same map? The answer is no. We will not get the same map. Because here it will be dolomite plus quartz surely, but you can see the whole reaction now occurs only at this temperature, not over a temperature interval. Not over a temperature interval. So you will have this dolomite quartz field, and then you will have quartz tremolite calcite field. Quartz tremolite calcite field. But this assemblage, so you will have dolomite plus quartz field, and then you will have quartz tremolite calcite field. Have you understood? But this assemblage here, which is dolomite, quartz, tremolite, calcite, that will occur only along this line. This is the line where you have dolomite, quartz, tremolite, calcite. The four assemblages will be pencil sharp. They will have pencil sharp assemblages. So what will happen is, you will have in this diagram several contact oleols. Several contact oleols, and if you take it, then these, all of them will be dominated by low variance assemblage. Low variance assemblage. Why? Because high variance assemblages only occur at a particular temperature, where this path intersects the univariate reaction. This path intersects the univariate reaction. So what will happen is, this reaction will occur only at a single temperature. It will not occur over a wider temperature range. It will not occur. So the low variance assemblages here are wider. But for this type of a situation, your low variance assemblages will be razor sharp, knife edged low variance assemblages. But it will be dominated by high variance assemblages, such as the assemblage at this part, the assemblages in this part, the assemblages here. But these assemblages will be present by a very special temperature, and which will occur at very sharp intervals. So you will be dominated by bivariant assemblages, which will be separated by razor sharp, knife edged low variance assemblages. Almost they will not be visible with the naked eye. You have to be very, very careful to find out the low variance assemblages which are drawn in red. But the bivariant assemblages, they will be very, very common. In both the cases, the high temperature assemblage would stabilize closer to the bathyl, but there will be a difference. So if you mineralogically map around contact areoles and rocks which have the same composition, then, and if you can map these bands, you will be able to tell immediately whether you had a closed system or a open system situation. In an open system situation, low variance assemblages will occur as knife-edge sharp boundaries, and they will separate high variance assemblages. Here, low variance assemblages should be wide, should be wider, and even within the wind, say for example here, dolomite and quartz will go on decreasing, and here tremolite and calcite will go on increasing, because that is what exactly happens along this temperature band. But here that band is missing. So this is a classic case of closed system metamorphism. This is a classic case of open system metamorphism. Now, normally what happens to make our life miserable, these two end members, like closed system and open system, nature does not work in extremes. Nature works somewhere in between. So when you have in-between situation with both closed and open system situation working, then you can see you will be a combination of these parts, and mapping of this will not give you smooth continuous lines, but it will give you very scrappy, very uneven surfaces which will not follow the smooth surfaces of the batholiths. It will not follow it. So the two end member processes can be easily separated on the field, but if you have intermediate members, where for example in several areas it has been shown that there was a closed system metamorphism where fluids were pumped in pulses. It can be mapped, but those are essentially theoretical deductions. But part of it can also be mapped. So I think that is what I wanted to say. I will make this class brief a little bit, because I think overall I have taught you what I wanted to teach you. So most of this I think you can read it from the book of Philpotts. It's given in great detail, so you can read about it. And we will from the next lecture, we will switch over to something else. For the moment, I think this is all for metamorphism of siliceous dolomite and dolomitic quartzites and all variations within that. We can do it. A high temperature, very high temperature assemblages. Remember that when you have a batholithic intrusion in such a situation, your low temperature assemblage should be away, and the high temperature assemblage should be in the inner areole of the metamorph, inner areole of the closest to the batholith. You will have the highest temperature. So maybe at the batholith you will have lustrite. You will have a lustrite. If there was calcite and quartz surviving after this, you will have lustrite at the immediate contact with the batholith. Otherwise, you will not have lustrite. And this part, inner part, will be dominated by phosphorite dioxide assemblages, whereas the intermediate parts will be dominated by tremolite, and further off will be dominated by dolomite plus quartz. But the question here, while this pattern would not change, yes, again, wollastonite will be at this point, high temperature assemblages closest to the batholith and low temperature. So overall it's the same. But low variance assemblages will occur as razor sharp, separating higher variance assemblages in closed system, in open system metamorphism. In closed system metamorphism, high variance assemblages will also form bends, because they represent a zone of temperature. So they also will form bends and will be flanked by high variance assemblages on either side. Here, the low variance assemblages would be lines. Okay, then I stop here today. You can read it from the book by Philpotts, and what is the name of the person? Yeah, Philpotts and Agnew. Yeah, Philpotts and Agnew, and there is a very detailed description of that. So I think you will get it. We will switch over to another topic in the next video lecture. Thank you.